Students, now we are going to solve problem in properties of pure substance and application for open systems. So what we earlierly studied in the first unit, there is a application of open system. So that is again we call it as that condition is called that is called as a steady flow energy equation. Already you know that steady flow energy equation is again solved in the third unit with the help of a steam tables. The problem especially related to expansion of steam in a nozzle. Okay. Okay. Now we move to the problem. Here the steam enters isentropically in a nozzle at a 250 degrees Celsius, sorry, at 10 megapascal, 1 megapascal and 250 degrees Celsius to 10 kilopascal. The steam flows rate is 1 kg per second. Find the velocity of steam at the exit from the nozzle and the exit area of the nozzle. Those two things we are going to find. Neglect the velocity of steam at the inlet of the nozzle. So first, how we can approach the problem? So we can approach the problem by drawing a one nozzle. Okay. So the nozzle is insulated. Nozzle is insulated. The steam flowing condition, that condition is called as a 1. Then exit condition, this condition is called as a 2. So the steam enters in a nozzle at a pressure, say that is a P1, which is equal to 1 megapascal. So we can convert a pascal into bar. 1 megapascal is 1 into 10 to the power of, say, that is a 6 pascal, which can be written as 1 into 10 to the power of 5 pascal. So 10 to the power of 5 pascal, we call it as, sorry, 10 into 10 to the power of 5 pascal. The 6 can be split up into 10 and 10 to the power of 5. So we call it as, that is called as a 10 bar. So P1 is equal to 10 bar. Then another condition, the temperature T1 is equal to 250 degrees Celsius. That is another one condition. Then mass of enter, that mass of one which is equal to 1 kilogram per second. Then it can leave from the turbine at a rate of at a pressure of 10 kilopascal. So P2 is equal to 10 kilopascal. So we can be written as in terms of power, that is called 0.10 into 10 to the power of 2 kilopascal. Kilo we can be written as that is a 10 to the power of 3. So 10 to the power of 3, 10 to the power of 2, 10 to the power of 5 pascal. So 0.10 into 10 to the power of 5 pascal. So 10 to the power of 5 pascal we call it as bar. So that is called as 0.10 bar. Okay, that is a P2. So these two things are given. Then what the parameter that we are going to find is, the question in a problem, the parameter we are going to find is C2. So what about the velocity of nozzle exit? Then what about the outlet area, that exit area of the nozzle? These things we are going to find. So after that, the second part of the problem is, then the exhaust steam from the nozzle enters into the condenser. So the steam that can, after the nozzle, it enters into this part that is called as a condenser, enters into the condenser and flows out at a saturated water. So this portion is called as a condenser. Here the cooling water that may be entered into the condenser. The outlet condition is called as a saturated water. Here the pressure is same, because normally condensation takes place at a constant pressure. So we call this position is, that is called as a 3. We call the position is 3. So P3, which is equal to, again that is a 0.10 bar, because normally the condensation takes place at a constant pressure. The cooling water in the condenser enters at a rate of, the cooling water enter at a rate of, so 25 degrees Celsius and leaving at a 35 degrees Celsius. So the cooling water enters into the coil, it absorbs the heat from the steam and increases to 35 degrees Celsius. The steam is, again it is coming as a saturated water. Steam is fully converted into saturated. Here we are going to find what about the mass of cooling water that enters into the enters into the condenser to cool the steam from the what saturated water. So before that, before entering into the problem, you know what is the condition of steam at 1 and 2. So for that we are going to see the TV diagram. So temperature volume diagram. In a temperature volume diagram, we are having that curve is called as a saturated curve. In a saturated curve, we have constant pressure lines. Sorry, these are the constant pressure lines. Okay, here the nozzle works in the two pressure. So one pressure is nothing but that is called as a 10 bar. Another one pressure is equal to 0.1 bar. So in a 10 bar, what is the saturation condition? In a 10 bar, what is the saturation temperature? So in a pressure table, in a steam table, you go the pressure table at a 10 bar pressure. What is the saturation temperature? The saturation temperature is 179. So the Tsat is equal to 179. But the given temperature is 250 degrees Celsius. So the given temperature is T given or T1 is equal to 250 degrees Celsius. T saturated is equal to 179. So at a 110 bar pressure at a 250 degrees Celsius, the steam is above saturated condition. So we are going to write, so T given, otherwise T1 greater than T sat. Because the 2 T given or T1 which is equal to 250 degrees Celsius greater than 179.8, 179.9 degrees Celsius. So the given temperature is given than saturated temperature. So the condition at the condition of substance is that is called as that is superheated steam. Superheated steam. So this is a point number one. This is a point number one. So from the steam table at a 10 bar the saturation temperature is 179. But the given temperature is 250. So finally you know that the steam is superheated. Why? Because so it is starts from 179. So it's 100 it is no value, 150 it is no value, 250 is only given. So after 179 the value starts. After 179 the value starts. Okay, so the temperature given is 250, so definitely it is superheated steam. This is the first clue you have to find, the entry condition of steam is superheated. The second clue is in a pressure table. In a pressure table at a 10 bar, the given temperature 179. So definitely from the relation you have to find the steam entered is a superheated. Okay, there is you find it from the steam table. So this is a pressure table. Here this is a pressure table. In a pressure table at a 10 bar condition, this is a 10 bar condition. The value that may be given as 179. That is the saturation temperature. Given temperature is 250. So definitely T given is greater than, that is a T saturated. So 250 is greater than 179.9. So the steam is superheated. This is a clue I have to find entry condition that is called as superheated. What about the condition at a 2? Whether the 2 is saturated or wet steam. So a nozzle then expands isentropically. The problem is given as isentropically. So there is a line is straight line. So line is straight line. This is a point number 2. So we call it as in a TV diagram we call it as that is S1 is equal to here, sorry, that is called the TS diagram. We consider S1 is equal to S2. So at which pressure the steam is up to which pressure the steam is expanded, this is called 0.1 bar. After that the steam again which is cooled to what? Cooled to saturated state. This is a point number 3. This is a point. This is a point number 1. This is a point number 2. This is a point number 3. So 1, 2, 3. So you know one may be a wet or saturated. How we can find this condition? So for finding a wet or saturated, you know wet or saturated, you need the dryness fraction at a point number 2. First you have to find the dryness fraction. Okay. Here. So that is called here the problem. The expansion in a nozzle is called as a isentropic expansion. Isentropic expansion because in a nozzle, this is a condition number 1, this is a condition number 2. So isentropic expansion, we call it as, that is called as a S1 equal to S2. So first you find S1. So at point 1. So point 1, all where exists already from the case point 1, that may be a superheated steam. So point 1 is a superheated. So superheated, you have to find the values. So in a superheated stable, it is a 10 bar at a 250 degrees Celsius. This is the enthalpy, and again the 10 entropy in a specific entropy of superheated steam. This is a specific enthalpy of super steam. Specific 10 bar 250. This is the value. So the H1 is equal to 2. Sorry, not this one. This one. 2943.0 kilojoule per kilogram. Then S1 is equal to, what is that, 6.926, 6.926 kilojoule per what, kilogram Kelvin. Okay, already you know S1 is equal to S2. So at point 2, where exists. So at the point 1 it exists at a, that is called as a 10 bar. At point 2 exists at a, that is, a pressure is equal to 0.1 bar. So at a 1 bar, at 1 bar you are going to, this is at 1 point, so point 1 bar, this is given there. I am unable to write there. There is a point 1 bar. So what about the SF and SG? At a point 1 bar, SF is equal to 0.649, SFG is equal to 7.502. Similarly, HF equal to at 191.8, HFG which is equal to 2392. Unit you can write, there is a kilojoule per kilogram. Here it is a kilojoule per kilogram Kelvin. Okay, all right. So after that, you may equate the equation. So S1 is equal to S2 because it is called as isentropic expansion. So in a normally TS curve, this is saturated. So this is a point number 1, this is a point number 2. So we can return S1 is equal to S2. So S1 superheated steam, already find this is the value S1. Here also you can write that is 6.926 equal to S2. We don't know S2 where it is located. It is located in a saturated or wet condition. So S2 you can be written as, that is called as SF2 plus X2 into SFG2. So 6.926 equal to SF2. SF2 we have a value here which is equal to 0.649. That is 0.649 plus X2 into SFG2 7.502. After substituting this value, you may get that is X2 is equal to 0.8367. This is a condition at the steam at exit, which is equal to 83.67 percentage what, dry steam. Okay, so normally in the diagram, so the two that may be located at 83 percentage. So this is almost nearer to the saturated vapor condition. Okay, then after finding X2, we are going to find the H2. Why we are going to find the H2, we'll explain in later. Then what is the necessity of H2 here? I will this also explain later. So H2, so point 2 after concluded, point 2 is in wet condition. Point 2 is in wet condition. So for wet condition, you have to find H2 is equal to HF2 plus X2 into HFG2. So HF2, the value, because 2, that is a 2 is a pressure that may be at a 0.1 bar, because so this is a line at the pressure 0.1 bar. So 1 bar pressure it exists. So 1 bar pressure, that HF2, then HFG2, you can write that same value earlier written as 190.8 plus 0.8367 into HFG, which is equal to 2392.9. After that, we may find that H2 is equal to, that is a 2193. After substituting the values, you find that is H1 is equal to 2193. So what is the necessity of finding H2? Okay, here the necessity of finding H2 is to find the velocity at the exit of the nozzle. So Now we going for the first law, that is application of first law in SFE, steady flow energy equation. So steady flow energy equation is written as, that is a m1 into h1 plus velocity, it can be written as c1 square by 2 plus z z1 plus or minus q is equal to m2 into h2 plus c2 square by 2 plus, sorry, plus gz2 plus or minus w. Here we are going to cancel the terms. So potential difference, that is not given 0. It is a isentropic friction, there is a nozzle, that is a 0. So work is not done in a 0. This was 0. Gz2 is equal to 0. And one more thing in a problem, the inlet velocity, neglect the velocity of steam at inlet of the nozzle, that is called as a C1. C1 is also neglected. So C1, the terms also neglected. So after the cancelling this term, the value became, so m1 into h1 equal to m2 into h2 plus c2 square by 2. Here m1 is equal to m2 is equal to m, which is equal to 1 kilogram per second, because the mass flow rate is 1 kilogram per second given in the problem. So this equation became h1 is equal to h2 plus c2 square by 2. So here it can be written as c2 square is equal to h1 minus h2, c2 square by 2 is h1 minus h2. So again c2 square is equal to 2 into h1 minus h2. So c2 is equal to square root of 2 into h1 minus h2. Okay, so here we have some term, just wait. Here we have one confusion here, because you note that here the velocity, unit of velocity c2 square is equal to meter square by second. The enthalpy unit is kilojoule per kilogram. So how we can balance this equation? So this is for c2 square, then this is for h. How we can balance this equation? So in earlier we have a conversion to convert the kilojoule per kilogram into meter square by second square. How we can be written as? So here kilojoule per kilogram, which can be written as, joule can be written as Newton meter divided by kilogram. So here what is unit for Newton? The Newton can be represented mass into acceleration. So kilo mass into acceleration, and what is unit for acceleration? Meter per second square into meter divided by kilogram. So kilogram getting cancelled. Then kilo, that have meter square by second square. So we are getting kilo, that is called meter square divided by second square. So kilojoule per kilogram is equal to, so again kilojoule per kilogram is equal to 10 power 3 meter square divided by second square. Okay, so for that the unit is, note that the unit of enthalpy is equal to kilojoule per kilogram. So for kilojoule per kilogram, we substituted as, this kilojoule per kilogram is substituted as 10 power 3 meter square divided by second square. So kilojoule per kilogram is converted into this value. So now we substitute the values. Now we substitute the values. Sorry. C2 is equal to square root of 2 into what is H1? Sorry, H1, which is equal to what? 2943. H2 is equal to 2193. 43 and 2193. Here, so into, that is called as a 2943 minus 2193 into 10 power 3. Okay. So after substituting the values, we are getting velocity which is equal to 1224 meter per second. So the velocity at the exit is 1224 meter per second. The first part of question, which is equal to completed. That is the exit of the nozzle 1224 meter per second. Then we are going to find the exit area. Then how we can find the exit area? So the exit area can be found with the help of a relation. Already you know the relation, that is a continuity equation. Mass at 2 is equal to, that is a area into velocity into specific volume at 2. So from that you have the relation, you have going to find A2 is equal to m2 into specific volume 2 divided by, that is called as a velocity 2. That is the relation. Okay. So for that you have to find the specific volume at 2. So how we can find the specific volume at 2? So specific volume at 2, that is V2 is equal to V of 2 plus x2 into V of G2. Here V of 2 already at a 1 bar. The V of 2 is equal to, here it is 0.001010. X2 you find, that is already you find 0.8367 into V of G2, that is Vg minus Vf. Vf2, that is called as a, we can written as Vg minus Vf. So Vg value is given, Vf value is fine. After substitution, you are getting the V2 is equal to finally 12.27 meter cube per kilogram. This is the V2. Okay. Here there is one issue in the relation. I will say there is one clue in the relation. Here written as, I am written here. Please note that V2 is equal to Vf2 plus x2 into Vfg2. So here it can be written as Vf2 plus x2 into Vfg2 can be written as Vg2 minus Vf2. Listen, here this Vf2 plus x2 into Vg2 minus x2 into Vfg2. In some cases, V2 is equal to x2 into Vg2. This is the case. Many problems that can directly take this formula. Why this formula is, here this Vf2, this, sorry, not, I can made one mistake. This is the what? This is a Vg2 Vf2. So Vf2 x into Vf2, that may be, the significance is very small. Why? Because you consider this equation. So 0.001010 plus x2 0.83 what? 67 into 14.675 minus 0.001010. You can find that. You can, the difference of 14, you minus the 0.001010 from 14.165. Finally, you are getting this value is equal to 0.001010 plus 0.8367, 14.674, 675, 674. That is the difference. So that's why this value is 0.0010, that is negligible. So finally, this is the key value. So that is called as x2 into, that is a Vf2. 14 point, that is Vf2, that is equal to 14.67. So sorry, Vg2 14.67. So this Vg2, there is a key value. So this Vf2 is very much low, 0.00 something. So that is maybe like negligible. So finally, many studies directly V2 is equal to x2 into Vg2. So we can substitute x2 into Vg2 with x2 is equal to 0.8367 into Vg2, which is equal to 14.675. Here also you can get the value which is equal to 12.27. So here V2 is equal to 12.47, that is a meter cube per kilogram. Here also the value is 12.27 meter cube per kilogram. So from that relation, this V2 is equal to F2 x V2, which is equal to V2 x So both are same. This one and this one are same. Okay. Now we find the V2. Substituting V2 in the area. So already we know that is A2 is equal to M2 into V2 divided by C2. Here A2 is equal to M2 into V2 divided by C2. So M is equal to 1, N1 to 12.27 divided by what is the velocity? The velocity is 1224. 1224. Finally, you are getting the area is equal to 0.0100, that is called meter square. Finally, A2 is equal to 100 centimeter square. Otherwise, it can term in terms of meter 0.100 meter square. Then you find A2. Okay, here the second part of question, that exit area, that is fine. That was fine. Then next we move to this part, this condenser part, that area after 2 to 3. So 2 to 3 are going to find. Here, listen, in a 2 to 3, it is the condenser. On that, this one is the condenser. This is the condition number 2. The exit is condition number 3. Here, some water, that water may be enter, so which entered as a 25 degrees Celsius and leaving as a 35 degrees Celsius. Here the fluid entered at 2, that is a H2, already you find the H2 is equal to what? Condition at 2. Here the H2 you find 2193 kilojoule per kilogram. 2193 kilojoule per kilogram, that is a H2. Then leaving is H3. But the leaving H3 in a problem, it is given as, leaving condition is given as saturated liquid. That is called as a F. So at what pressure? 0.1 bar. 0.1 bar it may be exist. So at a 1 bar, what is the HF 191? So here H3 is equal to 191.8 kilojoule per kg. Okay, so here wet steam is entered into the condenser and it cooled and became a saturated liquid. Okay, here in the diagram it may be represented as in a PV curve. So normally the condition at a 2, this is a wet steam. Here it is cooled at a constant pressure, say 1 bar. This is a constant pressure line. So it is cooled at a pressure, say this is a point number 2. It is cooled in a constant pressure until it reaches the saturated condition. So saturated means F. So for that we are going to F, taken as a F. Now we substitute the equating this equations. So listen, how we can equate it? So M into H2 minus H3. So mass of steam at 2, H2 minus H3 means heat loss due to enthalpy. Because heat loss in terms of enthalpy, because of cooling, wet steam is converted into saturated liquid, is equal to mass of cooling water entered into the cooling coil. So mCp into delta T. So here mass is 1, H2 already you know 2193 minus H3 which is equal to 191.8 equal to mass of cooling water. Specific heat of cooling water you already know that is a 4.187 kilojoule per kilogram degree Celsius into delta T. Delta T is equal to 35 minus 25. What is the unknown in this equation? So this is the unknown in the equation. All the remaining values are known because, so what are the heat lost by steam is taken by the cooling coil. So that is a heat lost by the steam is equal to heat gained by the cooling water. This is the steam, this is for steam and this is for cooling water. So after substituting all the values, you note that mass of cooling water required is almost 47.5 0.49 kilogram per second. This amount of cooling water is required for converting wet steam into saturated liquid, and when the inlet temperature is 25 and outlet temperature is 35. This amount of water is required. So this is the balancing equation. This balancing is important. That is, the heat loss by the steam is equal to heat gain by the cooling water. Okay. I think this is the entire sum that may be asked in 16 mark. In some part of sum that can be the first part of sum up to this one may be asked in 8 marks or 10 marks or 12 marks. The second part combined to form a 16 marks. So that is, the first part is a nozzle, second part is a condenser. So here the first part nozzle, then second part is condenser. So nozzle and condenser to form the single problem. Okay. The specific thing in a problem is, first one, you have to find the steam at the inlet, whether it is saturated and superheated. Then second thing, you have to find the dryness fraction, and then after application of SFE for this problem, then important factor is, don't forget to multiply 10 power 3 for conversing of kilojoule per kilogram into meter square per second square. So 1 kilojoule per kilogram is equal to 10 to the power of 3 meter per second square. So this is a significant part in the problem. Everybody did mistake in this part because they don't know to convert the kilojoule per kilogram into meter square by second square. Simply roughly substituting the H1 and H2 without 10 to the power of 3. So this is the most valid point in the problem. Many students did mistake in the area. Then after that, you have to find V2. Then by equating mass balance or heat balance, heat gained by loss by the steam is equal to the heat gained by the cooling water. So by equating this, we are going to find the mass of cooling water. Okay. Okay. Thank you. If you have any comments or queries, please feel free to mention in the comment box. That will use me for to solve the problem in the next session. Okay. Thank you.